Shall we start?
Sounds good.
I'm ready.
Okay, so it's my pleasure to introduce Tangi and Alexis, who will present the organization JuliaSmoothOptimizers at this JuMP NLP regular meeting. So Tangi, correct me if I'm wrong, but you are currently a postdoc at JRAD Montreal under the supervision of Dominique Orban. And Alexis, you are currently a PhD student, in the same lab, so JRAD Montreal, under the supervision of Dominique Orban as well, right? So you both have some specialization in iterative solvers, linear algebra, and numerical optimization. You're also co-developers of the JuliaSmoothOptimizers organization that you will present today. So I let you the honor to present your work.
Perfect. Thank you, Francois. And thank you all of you for the very kind invitation. I'll start, and then I'll leave some space, some time and some space to Alexis for the end of the talk. So it will be really 2 parts. And today I wanted to present what I call the roadmap for JuliaSmoothOptimizers, and mainly it's NLP Model API. So feel free to interrupt me if you have any question, and I'll try to give more details about that. So first, do you see my screen? Okay, perfect, awesome. So I'll start by thanking also all the GSO's contributors, and mainly Dominique Orban, which is our supervisor, and a lot of things in JuliaSmoothOptimizers are organized around his research team. And also thank Abel Suarez-Siqueira, who was a postdoc in Montreal and has been involved in JSO from the very beginning. And he's one of the leaders in the team. And he's now working in Netherlands. And all the other JSO contributors, really. So in this talk, I'll present the main features of the organization, JuliaSmoothOptimizers, and as I said, its modeling API, the NLP model. And mainly there will be 4 parts. First, I will briefly introduce the organization, then give some motivation, or at least my motivation, for the need of this unified API for nonlinear optimization. And this motivation in particular is to develop large-scale optimization solvers. And then I'll spend a lot of time actually talking about the NLP models, which is the API, to model problems. And the last parts, I'll hand over Alexis for presenting some examples on using NLP models on GPU, which I think it's a pretty cool application. I try to make sort of a figure of all the packages in JSO and some dependencies. So in gray, it's supposed to be external packages. So this figure is not actually even entirely updated, but it's a pretty fun thing. I'm pretty sure you'll have access to the notebook afterwards, or if not, feel free to send me an email so that you can zoom in and see if you are there already or not. Awesome. So I'll jump to the introduction of the organization. So as usual in JuliaSmoothOptimizers is a GitHub organization. As I said already, it's mainly organized around Professor Dominique Orban research team in Montreal. And mainly, I think our purpose is to develop linear algebra and optimization tools for developers, researchers, and academics. And we focus on nonlinear, non-convex, continuous optimization models. And on the most general problem I think we tackle here is the one I'm writing here, where we want to minimize some objective function. We have some constraints that are potentially nonlinear. And as usual, you have bounds on the solution also you are looking for. And very often we'll try to use derivatives of all the involved functions. So derivatives, first and second derivatives of f and c, mainly here. So this is the most general formulation. It will sometimes means that we are interested in unconstrained optimization, linearly constrained optimization, or quadratic problems. Okay, so this is just the most general framework. And so JSO currently provides 37 registered packages that includes solvers for optimization and linear algebra, also benchmarking tools, modeling tools, and test problems. So I try to make like tables with different categories and the names of the packages. So we'll focus mainly today in the models part. And so we are coding a bunch of things on our own in pure Julia, and also we are providing wrappers to other packages, okay? So that we are able to communicate between the external organization or languages and JSO. So we'll mention, for instance, we'll mention NLP Model IPOpt, which is a wrapper between IPOpt.jl and the JSO framework, and also mention NLPModelsJuMP, I think, in some minutes. Awesome. Also, you'll see, so we have a bunch of optimization solvers here, and also a bunch of tools for linear algebra. That's super important. These two categories are super important, I think. Awesome. And just to say a couple more words about where we are right now. So our main target is academic work, as shown in some references, but we are also starting to improve documentation to attract more users and contributors. In particular, I wanted to highlight the fact that we have a new website that includes tutorials, and we are writing a lot of them right now. And each package is starting to have docstring and tutorials. And we are making papers connected to the packages now. For instance, DCI solvers has been accepted in JOSS a couple of days ago. And also something very nice, since we are very connected to academia, the whole organization is also used for teaching. Okay. So in particular, this semester, we have a class on numerical optimization and optimal control at Polytechnique Montreal. Awesome. So that's a bit some general remarks about JSO. I'll go deeper in what we are doing. And I think one of the motivation for all this is to develop large-scale solvers for optimization, for nonlinear optimization. And so in JSO, since we are developing new solvers for optimization, what we did and what we have is we have a JSO, we have a set of rules that defines a JSO compliant solvers. And mainly it's not that heavy. It just means that all the solvers returns the same thing, which is a generic execution stat. You'll see what it is in a minute, which is defined in solvercourse.jl. We have a logging system and the same API to define the model. And this API is defined with the interface abstract NLP model. Okay, so more or less that's how it goes. Let's say I have a problem, and so here I'll use qtest. I'll say more about these different packages, but these two lines will define an abstract NLP model, and in particular one from the qtest test library. And I can use one of our solver. Here I'll use an LBFGS method available in the package JSO solvers. And that's it, more or less. So we have the logging, so it took a while here. But once you solve it, you can print the generic execution stat output and you have all the informations, okay? And what it's great is that if actually I want to solve the same problem, but with IPOpt, I can do the same thing and I'll get the same generic execution stat. Okay, so all the solvers can communicate together. And so yeah, that's the one. It's taking a couple of minutes. So you have the classical IP opt output, and then you see the generic execution step. So all these makes things easy, and then you can also benchmark solvers. So for instance, here I'll use the package solver benchmark that we developed with this aim, making benchmark. And let's say I'll compare two solvers, IPOpt via NLP Model IPOpt, which is a wrapper between IPOpt.jl and to make it use the NLP Model API, and DCI solver, which is a solver we coded in pure Julia within JSO that implements the dynamic control of infeasibility method, which is a sort of SQP, two-step SQP method, if you want to know. And so you need test problems. Here, again, I'll use Qtest. And what's great about Qtest is that it also comes with a problem selection facility. So I don't want to get into so much details, but here I'm selecting equality constraint problems with maximum nmax. So 300 here constraints and maximum 300 variables. I'm just removing some of these problems because IPOpt returns an error on them. So more or less, you have to define an iterator of problems. Then you define a dictionary with the two solvers you want. The solvers you don't have. You can do it with more than two. So you define dictionary with the different solvers you want, trying to make the tolerances fit between the two solvers. And then you can just call the bmark solvers, which is a function within solver benchmark.jl, and print some performance profile. Okay, so all this is, I think, pretty easy, pretty convenient, because all the solvers are following the same rules, meaning the same input and also the same output. So while we wait for the benchmark to finish, so you can extend this to different problems and different solvers. So in this table, I'll try to sum up more or less what we have right now. That can be split more or less in 5 categories for optimization. Nonlinear problem, in meaning the formulation I gave above, equality constraint problems, bound constraint problems, unconstrained, and quadratic optimization problems with linear constraints. And you have here in bold the solvers that are coded in pure Julia within JSO, and wrappers to others. Okay, so for instance, we have wrappers to IPOpt and Artelis Nitro as well. And the same goes for Cplex, Gurobi, and Express for quadratic problems. And then I mentioned DCI solvers, but there are more. Percival, for instance, is a matrix-free augmented Lagrangian method. And Canolis, another example, is a solver for constrained nonlinear least squares. Okay, so still waiting for the benchmark. And what's inside optimization? And I think that's super important as well. The main thing inside solvers, usually, one of the main tasks is to solve linear algebra problems. And we have a bunch of packages that are, I think, very good for this. For instance, for direct methods, there is LDL factorizations.jl, which is computing an LDLT factorization in pure Julia, or HSL.jl, which is a wrapper to the HSL Fortran collection. And also for iterative methods, we have Krylov.jl. This one is really complete. I think right now Alexis is working a lot on this, and so it's used by researchers now in linear algebra. It contains 32 methods that are tailored for very different problems, really square, rectangular systems, linear least squares, linear least norms, adjoint systems, saddle points, SQD systems, really everything, I think. And it's pretty complete. You have preconditioner, in-place function, and everything. Okay, and I think Alexis is working hard right now on adding support for complex numbers in Krylov, which is very advanced. I think this update is very advanced. Another thing we need when developing solvers for optimization is a good access to derivatives, and in particular, the most expensive thing is matrices like Hessian Matrix and the Jacobian Matrix. So we'll sometimes use, for solvers that requires the whole matrix, we'll need sparse Hessian and Jacobian matrices. And we are very often using CO matrix formats. And something else we need very often is an operator-ish way to compute matrix vector products. Okay, so Hessian vector products and Jacobian vector products without having to compute the whole matrix first. Okay, and so for these operators, we'll rely on linear-operators.jl, which is also developed within JSO. So I'm hoping we get the figure at this point, but probably not yet. A bit too fast. Okay. So the last part of this presentation that will be done with Alexis concerns GPUs. And also, I think at this point, it's worth mentioning that linear operators and Krylov are working with GPUs as well. Okay. So actually, Krylov is taking as an input more or less any type of matrix. And now we have the result of our benchmark. So just to show you the kind of profile you can make just with like 50 lines of code. I think that's pretty cool. Awesome. Is there any question so far?
So I have one question.
Yeah.
So you are mentioning that you can specify the linear quadratic structure of the optimization problem in NLPModels.jl, right?
Oh, sorry, I didn't really hear you.
Oh, is it my... Let me check. You mentioned that you can extract the linear quadratic structure of the optimization problem.
Oh, yeah. So extract actually is not the correct term. I'll be more specific in a minute there.
Okay.
No, so when we tackle quadratic models, let's say with linear constraints, we assume the user is telling us right away what's linear, what's quadratic.
Okay.
Okay. So I'll be more specific actually on how we model everything here in NLP model. So NLP model is one of the core package for our modeling structure, our modeling organization. It defines a unified API to access the model. Some model will provide sparse derivatives, so we have the API to access this. Some models will also provide matrix-free products, meaning that we don't explicitly use the matrix. And also, I believe the API makes creating new model an easy task. So really, what I hope you'll get from this presentation is that we rely on a predefined API, which is independent of the origin of the model. Okay, so in this small cell, I'm defining 3 times. I'm defining 3 times the unconstrained minimization of the Rosenbrock function. So first with Dnlp model, I'll tell more details about this different package in a minute, which use forward if to compute derivatives of the problem. Here I'm using qtest, or Rosenbrock is also part of the test problems in qtest. And I'm using JuMP and NLP model JuMP to convert the JuMP model in our framework. So again, with the Rosenbrock function. And then what we are using really afterwards is these functions, okay? So independently of the origin of the model, I can call the objective function, the gradient, the Hessian matrix in the same way, okay? So I can design solvers relying on this API, and and don't have to really care about the origin. Awesome. So what else is there in an abstract NLP model? Mainly it contains three things. First, an NLP model meta that contains the main metadata of the problem, meaning dimensions, the bounds, the number of non-zeros in the matrices, number of and indices of linear constraints. It also contains a counters that keeps track of the different evaluations of the functions in the API, and also it contains various functions. So you'll get, I think, what everybody expects from this framework in continuous optimization: access to the objective function, the gradient. Obfgrad will do both at the same time, as it is often frequent. Access to the Hessian matrix products, the operators that correspond to the Hessian matrix, and the Hess structure, Hess chord, is for access to the sparse matrix in CO format. And then you get the same for the constraint and the Jacobian of the constraints. Okay. Also worth mentioning that this API, when I'm talking about the Hessian matrix, it's the Hessian matrix of the objective function, but also of the Lagrangian function, okay, which is very often useful in optimization. So yeah, so just to show what's inside. So again, here I'm using a Dnlp model, which is pretty convenient. You just give it the objective function, an initial guess. Here I'm defining a constraint problem, and you have here the left-hand side of the constraints and the right-hand side of the constraint. So here we have an equality constraint, and it's equal to 0. And yeah, so just to show what's in the meta, you get a bunch of information, as I said before, and it's also written here in the next cell. So you get number of variables, number of constraints, and then ZG is the number of non-zeros in the Jacobian matrix. Same in the Hessian matrix. So by default, I think by default, the NLP model computes a dense matrix. Okay, so it doesn't check if the matrices have zeros. And you get everything else, more or less. Your initial guess that you provided at first, bounds on X, bounds on the constraints, number of variable constraint, number of non-zeros in the matrices, and everything. Okay, so that's for the meta. And yeah, so I prepared a bunch of examples of the API. This one, I think it's quite important. So the API also have in-place versions, which is, I think, a must now if you want to write efficient codes. So if you pre-allocated the vector G that will receive the gradient, you can use in-place functions. Okay, so it exists for the gradient, but also for all the other functions, really. As I mentioned before, you can access the Hessian matrix in CO format. So Hess structure will give you the rows and columns where you have non-zeros elements, and Hess chord is the values that are there. Okay, so here it's the objective function at X, and you can have some constant in front of it. Okay, so that's our obj weight. Also, you can access the Hessian directly, and since the Hessian matrix is symmetric, mainly we only store the lower triangular of the matrix and return the symmetric object. Okay, so it acts like the whole matrix, but only store half of it. And so as I mentioned, you can also have access to operator way of representing the matrix. So here, when there is an X and an Y, it's for the Hessian matrix of the object. Okay, and so it returns a linear operator. And then you have two ways essentially to compute matrix vector products. Either you use this operator that you just computed, multiplied by V. So since it's a lazy operator, like computing the operator here almost costs nothing. and all the operations are delayed until we compute the products. Or you can call the hprod products directly, okay? Also, same applies, so you have in-place versions of all this. And then once you did a bunch of functions, once you evaluated your model a bunch of times, you can access counters on how many times you call the different operations, okay? So that's what we are using, for instance, to make our figures, our benchmark figures, okay? As I showed before, okay. Awesome. So that's pretty basic things about NLP model and how really it works. Now I want to make a couple of different comments around that. The first one is that very often in Julia we want to use multi-precision models. So a key feature is the possibility to use different types. So let's say I don't want to run computations in float 64, which is the default in Julia, but I want to choose a different type here, float 32. I can, using Dnlp model again, I can define a model in float 32. Okay, so the objective function doesn't change. Only thing that really changes is that your initial guess must be a float 32 vector, and same goes for the left-hand side and right-hand side of the constraints, okay? And so this is the same problem as before, HS6, but in float 32. And so what's great then is that when you call the objective function or any function in the API, it's type stable. So the objective function will return something in float 32 as well. And the gradient will return a gradient in float 32, okay? So trusting the user or the creator of the model, if there is no crazy conversion inside it, you can run all the computations in float 32. And in particular, if I'm now giving this model to DCI, it will return a float 32 solution, okay? And we'll make all the computation inside it in float 32. Okay. Awesome, because in particular DCI doesn't rely on or only uses codes made in Julia. Okay. Awesome. So this will come in a couple of seconds. So I think that's one of the big feature and one of the reasons we want to develop new codes in pure Julia as well. So yeah, you get some solutions. So here the solution is one. It's a pretty simple problem. And so DCI did all the computation in float 32 and returned a float 32 vector. Awesome. So as I mentioned before, what's great is that solvers don't rely, are really independent of the origin of the problems. And so depending on your application, depending on the type of the problem, you can design a new NLP model, okay? So let's say I'm interested in nonlinear least squares, which is very frequent in practice. And the particularity in nonlinear least square is that the objective function is the norm square of some residual function, okay? So very often you will want access not only on the objective function or the gradient of this function, but maybe you'll want access to the residual directly or the Jacobian of the residual or the Hessian of the residual, okay? So here we have a tailored model for this. And so before I was using Dnlp model, here we have an Dnl model, where instead of giving the objective function, you give the residual function. And for the sake of avoiding an extra evaluation, you also give the size of this residual. Okay, and what's great is that you can access the residual separately. And I think I'll show that. You can also access the Jacobian of the residual separately. Okay. So it's not obvious here, but since the AGNLS model is also an abstract NLP model, we could ask for the objective function or the gradient of the problem as a classical NLP problem, okay? And it works for nonlinear problems. It works also for linear problems. So here I'm using LLS models package, which defines also the API for linear least squares. And so for linear least squares, you expect to have a matrix and a right-hand side. And here it goes. Okay. So when I'm saying a matrix, it's really in math term. It could be any type that corresponds to a matrix. Okay. So here my matrix is actually just an operator in linear operator format. Okay. And since it's a linearly square, I can solve it with Krylov methods. And here, for instance, using CGLS, which is a variant of the conjugate gradient for this type of problems. Awesome. So that's for least squares. So I think you get the spirit a bit now that for different type of applications, we have different packages. And one that I really like is the following. It's called Pd-Nlp Model. And I'll show this model, yeah. And it's designed for optimization problems with PDEs in the constraints. And the idea is that we'll use GridApp.jl to discretize using finite element methods the PDE. And then implement the whole NLPModel API, okay? So this is one example of a distributed Poisson control problem with Dirichlet boundary. So you get two variables here, the y, the unknown of the PD, and u, some control function. And then you get this PD, the boundary condition here, and some objective function where yd is a given target. And so here it's a norm actually. And yeah, you want to minimize this term. So it's a pretty classical problem. And the idea in this package is that we use GridApp to discretize the PD and discretize the functional space. And we implement the discretized problem, okay? So then the rest, most of the modeling is using GridApp's interface, which is also coded in pure Julia. So as you can expect, you'll have to provide or describe what you want, how you want to describe the whole space. So here it's the square minus 1, 1, and you provide n to be the number of discretization points you want. So I'll try not to be too crazy for this presentation. Then you will have to define the different spaces, the functional spaces. So you'll recognize some things that I mentioned. So I wanted Dirichlet boundary condition. So you have some tags for this. You can specify the smoothness of the unknown functions. And so it was Dirichlet boundary equal to 0 at the boundary. So you'll get this type of function, okay? And what's important in GridApp is that you give things in weak formulation. So you have to precise what you mean, how you compute the integrals, how you approximate the integrals, and then really define the function, the different functions, okay? So the objective function and the operator, the PDs in its weak formulation, okay? So I really like the GridApp interface where you actually write the integral sign and the measure sign, really like you are writing math. Awesome. So that's the GridApp part. And then you can define a GridApp Pd-Nlp model. So that's what's implemented really in Pd-Nlp And this implements the whole abstract NLP model API using the GridApp model. Okay, so this will take a couple of seconds because even though I chose a small problems, it always takes some time the first time. Awesome.
Maybe
and
while
since,
that's starting, I had a question for something earlier. How do solvers know if they support a particular model? Is there some kind of way to tell the user you chose, you picked a nonlinear least squares model, but then you gave it some solver that didn't know about that?
So we have then tailored solvers for each of these problems. So I don't know if this will exactly answer your question, but so we have solvers tailored, for instance, for nonlinear least squares. But what's great is that then you can just compare these solvers with IPOpt, for instance. And IPOpt will just not exploit the fact that it's a nonlinear least square. So does it?
Okay, but then but then if you give the nonlinear least square solver to some generic, just standard nonlinear program, it'll say, I don't know how to deal with that.
No, so yeah, unless the solver has some internal mechanism that can switch from, that can sort of detect the type of the model, you won't know. So we have, for this specific example of the nonlinear least square, we have an abstract NLS model type. So it could detect this. Actually, that's what we do when interfacing with Nitro. So in NLP model Nitro, it checks if the problem is an abstract NLS model. And if it is, it does something different than if it's a classical nonlinear problem.
Oh, nice.
So it's not fully automatic, but I think, yeah, so that's it. And that's something we are actually, I think, doing if the solver has linear constraints. I think Nitro, IPOpt, I don't exactly remember if they have some special features. If you have linear constraints, they will treat that differently than linear constraints. So that's ongoing work. So it's pretty long, but you'll get the spirit now that I have my GridApp Pd-Nlp model. It's just a nonlinear model as any other, and I can use DCI. I was hoping. So we'll wait a bit, and so you get the same thing. Okay.
So is that time the solution time, or is that all latency of compiling all the packages?
So it's time, because so what's a bit slow here is the GridApp machinery, but also the first time you initialize the model, here we compute more or less the structure of the Hessian and Jacobian matrices at first. So so this is sort of expensive because you'll have to go over the whole discretization to see where there will be non-zeros elements. That's why it's a bit slow, I think.
How are you doing that? Is it on the GridApp interface, or is it inside Pd-Nlp model?
Sorry again, I didn't really hear.
No worry. How are you computing the initial Hessian and Jacobian?
Why or no? So I'll try to answer also. I didn't fully hear you. Yeah, so that's also, this will help explaining. So since we'll want to have access to the Hessian and Jacobian matrix in sparse format, you'll want to allocate the structure for this to know where you have non-zeros element. And in particular here, what I'm showing, this entry nlp.meta.nnzh is the number of non-zeros element in the Hessian matrix. So since we are computing all this information first, it takes a bit of time. But then it's something you don't have to do again, or something you don't have to store again when you compute the Hessian or the Jacobian afterwards.
Is this information provided by GridApp, or is it computed inside the Dnlp model?
So yeah, no, it's not given by GridApp directly. Also, what's slightly different here compared to what GridApp does, just to show the parallel. So GridApp doesn't handle the control function So we are sort of extending it for that. Okay, so it's really following what GridApp is doing, and yeah, maybe actually it returns that. Yeah, it doesn't do everything, but it does a pretty great job with the discretization. Awesome. So yeah, so that's more or less that I wanted to show. Well, we'll get the results, but as you will expect, this year I will find some solution. Otherwise, I wouldn't show this example. So that's great because earlier I showed an example where this year I solved an Dnlp model, and now it's a Pd-Nlp model, and it works the same way. Okay, so obviously for full optimization, for full performance, you'll have to find the best match. For instance, let's say if you have a model where you can conveniently access the matrix vector products as an operator, and you have a solver that doesn't use that, it's a bit sad. While you could use matrix-free solvers, for instance. Okay, but that's always the case. You have to find the best match. And so this shows counters. Here, though, so we see that we evaluated the objective function 4 times, the gradient 4 times. So the rendering is a bit weird. So we evaluate the whole Jacobian matrix twice, as well as the Hessian matrix twice. And we did a bunch of Jacobian vector product and transpose Jacobian vector products. So this is because DCI actually is a 2-step process, and it has a matrix-free feasibility step. Okay, so to find a feasible point, it's matrix-free, so that's why it makes a bunch of products with the Jacobian matrix. And then the tangent step is computing the whole matrix. And then, so I didn't really mention that, but the output of the solver, the generic execution stat, gives a bunch of information on the problem. And for instance, you get the primal feasibility, which is how much you respect the constraints, and the dual feasibility, which is more or less the gradient of the Lagrangian function, which are pretty small here, which is good news. Awesome. So that's for Pd-Nlp model, and really we are doing this for more. And this is a sort of a table showing how it works. So everything starts from NLPModel.jl that really define the abstract API, and this package doesn't really contains it doesn't contain any concrete definition of a model. Okay, just describe the whole behavior, and all the solvers rely on this behavior. And then you get a bunch of packages connected to that, NLP model modifiers that transform the problems in different variants. I'll say a couple of small word on this. And we implement a bunch of different models depending on the origin of the problems, okay? Depending on how we get them or what are their characteristics. So in interest of saving some time, I'll skip what's inside NLPModel.test.jl, but since we have to define different new models for different applications, we have a bunch of unit tests defined here. And then modifying models that are available in NLP model modifiers. I think it's pretty cool for people working in numerical optimization. Let's say you have an optimization problems and you want you want it to be a problem with equality constraints and bound constraints only, then you can use the Slack model to transform it. Or you just want to find a feasible point of some problems, then you can use feasibility residual to define a nonlinear least square that minimizes the square norm of the constraint function. And it goes like this on and on, okay? Also, we have quasi-Newton models. For instance, that's what we use in the LBFGS implementation in JSO solvers. Okay, so that's super easy actually to convert one model to another one. And again, independently on the origin of the problem. And we have more. I'll skip some of that, but manual NLPModel.jl shows how to implement and manually provide all the functions. So if you know the Jacobian matrix or you know the Hessian matrix, you can actually precise everything. And that's something we use in our implementation. For instance, if you want to develop a penalty method, there will be an NLP model that corresponds to the penalized subproblem. Okay, so that's what we use in Percival.jl, where we define an augmented Lagrangian model that corresponds to the penalized subproblems. We have wrapper with ample NL readers. So you have quadratic models.jl for quadratic optimization with linear constraints. NLP model JuMP that converts a JuMP model as an NLP model. And we have a variant in particular for NLS model. So the hack here is that we define the residual function as an expression or NL expression, and then we build the whole thing. And the last one that I like a lot, I show a couple of examples already, Dnlp Model.jl that implements the NLP model API and computes the derivative using automatic differentiation. And this one is great because you can change the type as you want. And what's also great is the flexibility in the input in the functions you give. And following some recent updates, and I thank him for that, from Mohamed Tarek, it now contains a backend system that allows using different AD systems. So by default, you can compute derivatives with forward diff, reverse diff, and zygote. But you could tailor the backend to mix things up. And we are also actually investing a lot of time there to improve the performance of each backend and also to compute sparse Hessian and Jacobian derivatives. So actually right now, right now we compute only dense matrices there, which is not convenient, but that's ongoing work. And then more or less packages like Dnlp Model are, I think, the perfect match for multi-precision solvers. That's one of the things we are interested in right now, meaning solvers that are switching the precision as the iteration goes. Okay, so we are really exploiting everything here. So we have test problems. So also same for the sake of saving, sometimes I'll skip that, but we have one package that I like a lot, optimization problems.jl, that contains problems in Dnlp model and in JuMP format. So I think that will be very nice for benchmarking in the future. And it has a data frames that contains information on the different problems. Some of them are scalable, meaning you can control the number of variables and constraints. So this will return a JuMP problem with 50 variables. And you can do the same with Dnlp model problems. So he's stuck somewhere. Oh no, it's just, okay. So here you get the data frame, the JuMP model, and you can, just by changing n, you can get a different size. Okay, so not the number of variables here. And you can do the same for AD model. And what's great with AD model is that you can change the type again. Okay, awesome. And to finish, one of the things we are working on right now is to add linear constraints in the API, meaning I want to access separately the linear constraints from the nonlinear constraints. That's something which is already available in NLPModel.jl, and that will be very soon actually deployed across the whole organization. Awesome. So that's more or less it for me. I will hand over to Alexis for the NLP model GPU support. If you are still here, Alexis.
We have 7 minutes left. Just
okay.
I mean, we can always run later because the thing will be recorded if people need to drop off.
Okay, sounds good to me.
Okay. So I'll stop sharing probably and let Alexis share screen.
You just might want to zoom in a little bit, Alexis.
Okay. Is it fine?
Maybe a bit more. Perfect.
Perfect.
Thanks.
Okay. So for my case, I will explain how we can use efficiently the Hessian vector operator and the Jacobian vector operator, so that it doesn't form explicitly the matrix, like Tangi explained in the presentation, but only use function that compute Hessian vector and Jacobian transpose vector product. And we'll see how we can efficiently use that with some GPU. So for instance, I will present two basic optimization methods. So the Newton method, which is specialized for solving unconstrained convex function. And for that, when we want to use the Newton method, at each iteration, we need to solve a square linear systems, which is this one, where the matrix is symmetric positive definite. And if you use the Krylov method for solving this system, you don't need to store explicitly the coefficient of the Hessian. You only need an operator that will be able to do a matrix vector product with this Hessian. And we'll see how we can do that with a new NLP model, a basic NLP model, and the linear operator that are available with NLP model. So there I will define a very basic model. So I will call my NLP model, which is parameterized by two parameters, T and S. T is a floating point system, so it can be simple, double, or another floating point system supported by Julia. And S is a storage type. So it can be a vector of double precision if you want to solve the problem on CPU, but you can be also co-vector if you want to use NVIDIA GPU to solve your system. So there I will define my small NLP model. So you only have one parameter, the counters, and the metadata. And for this small model, I will define only the functions that are required for solving the problem. So I will define the objective. So a very basic function that work nice on GPU. I will use a forward if to compute the gradient. And for computing the Hessian vector product, I will use a directional derivative of the gradient. So I will not form the Hessian explicitly. I will only implement the Hessian vector product. And after, I will use the S operator, the Hessian operator of NLP model to compute the Hessian vector product. And because in all Krylov method, you only need to use the mul function, which is a matrix vector product, it will work without forming the Hessian. For instance, when I explain the Newton method, I said that I only need to solve iteratively some linear system of this form. And here, I will compute at a value of x my Hessian and my gradient and solve these systems. So there I will compute a direction of my linear systems. But if I want to minimize my function, I will need to solve a multiple system of this form inside the Newton method. And here I can implement easily a Newton method based on my NLP model and the basic function of the NLP package. So I only use the gradient. So for that, I use the forward if and my Hessian operator. So my Hessian operator is only based on the forward if, but there it will not form explicitly the Hessian. And after, at each iteration, I can solve these systems with my Krylov method. And at the end, it will return the solution of my the solution of my optimization problem. Everything is computed on GPU. So that's my first problem. And now I can show another example with this time an NLS model. For the NLS model, I will want to solve a nonlinear least square. And at each iteration of my Gauss-Newton method, I need to solve a linear least square problem this time. And for that, I can use, for instance, the Lsmr method, which is specialized for solving linear least square problem. And for that, we'll only need to model operators that can compute the Jacobian vector product and the transpose Jacobian product. I don't need to store explicitly the Jacobian. So I will define a new model, which is my NLS model, which is very basic. And for that, I will implement only 3 functions. So the functions that will compute the residual, so the components of my f function, and 2 functions that are used to compute the Jacobian vector product and the transpose Jacobian product. For that, I will do also directional derivative of my residual function and the gradient of a dot product that will be able to recover the result of the transpose Jacobian vector product. And after, with only this function, I can define an operator, which is a exact operator residual. And this function will internally use these 2 functions, this one and this one. And it will be transparent for the user because it will be defined as a matrix, but with this structure, we will be only able to use the mul function, but it's only that function that it requires by a Krylov method. For there, we can use Lsmr, and they will use only the matrix-free operators and function. And as above, I can implement my Gauss-Newton function, that is this time take as input NLS model. And for this function, I will only need the residual function and the Jacob residual function. And at each iteration, I will call my Krylov solver to solve the subproblem. And at the end, I will recover the solution. Everything is computed on GPU.
Very nice. So are there good performance benefits to doing all of this on the GPU?
Yes. If you, for my part, I'm mainly working on the Krylov method. And if you solve linear system on GPU, the difference can be a factor of 100 if the system indents, and between 10 and 30 if the system is sparse. So if you have efficient, you can say, efficient differentiation tools for computing the Jacobian vector product or the Hessian vector product, you can solve very efficiently optimization problem on GPU.
Okay, so the win comes from having that matrix free.
Yeah, and the opportunity to directly use an operator for that easily.
And how large are the matrices and vectors to get those performance improvements?
When I tested only the linear system on GPU, it was around 10,000 variable, begin to have good performances. But you can solve biggest problem easily on GPU. But around 10,000, we can begin to have something nice in performance, in terms of performance.
Nice. And have you done that for eigenvalues computation also?
No, I never tried for eigenvalue problems. Okay, but it could be nice too. I know that Francois developed a solver that uses the Krylov method, joint work on that. And I know maybe Francois, you can help me on that. What are the biggest systems that you solve with Krylov method?
So we're mostly solving sparse linear system.
Yeah,
I think the larger is maybe 100,000 times 100,000 square. non-symmetric, indefinite.
And the differences is also 100 with your GPU at Argonne?
It all depends on the preconditioner. I mean, the bottleneck soon becomes a preconditioner on the dot operation inside kernel.jl. That's another story.
Quickly, the main issue is on GPU, you have difficulty, you can access to coefficient of your matrix. So it's why we have difficulty to use direct method. And if you want to use Krylov method, sometimes if the system is big, you need to have a preconditioner. And the preconditioner is difficult to form without having access to the coefficient of the matrix. But it's another problem. Do you have other question?
If not, I'd like to thank both of the speakers today. This is super interesting. I think we have a few things to work on going forward. One thing we've been talking about in the chat is setting up a kind of MOI solver interface to JSO so that you could use any of your optimizers that you're writing as kind of solvers through JuMP. So it seems like you've already got a way to go from a JuMP model to a NLP model. But then kind of interfacing the solvers would also be nice. But with that, I will end the recording and we can stay online and chat more if we need to. But thanks for the talk.
Thanks.